Very good then. So it's a pleasure this week to introduce Avi Loeb to give the Origins Colloquium. Avi received his PhD in, I think, 1986 in Hebrew University of Jerusalem in physics, and then only later started to work on astrophysics when he was a long-term visitor at the Institute for Advanced Study in Princeton. He, in the early 90s, then went to Harvard as an assistant professor, where he is now the Frank Gabed professor, and he's been chair of the department there for many years as well, until 2020. Well, I was just looking on ADS, published more than 730 refereed papers. So one of these people who publishes more papers than I've ever read, seminal papers in a vast range of topics, everything from microlensing of planets to the first stars and galaxies to predicting plasma around black holes. And in particular, in first stars and black holes is where I've become most familiar with his work over the years. It really inspired me at the beginning of my career. He founded the Black Hole Initiative at Harvard in 2016, where there's a number of interdisciplinary topics on black holes being studied, and has been the director of the Institute for Theory and Computation at Harvard as well. So more recently, he's been working and interested in these interstellar comets, which are incredibly fascinating objects. And I think we'll hear about those today. So it's a pleasure to welcome you to the talk, Avi.
Thank you so much, Jonathan. Yes, it has been a while. I've been studying astrophysics. Just yesterday, I was interviewed on a podcast by a student, and she asked me, what is the fun of doing science? And I explained it with an example. Yesterday morning, I woke up and saw a paper that was just published in the Astrophysical Journal about the little red dots that the Webb telescope discovered. One of the puzzling discoveries, we see galaxies at the cosmic dome that are extremely compact. They seem to be redder than expected, and they emit more energy than one can accommodate with the lambda CDM cosmological model if you just account on use stars for the emission, and so they may very well have a black hole at their belly. And the question is, what are these little red dots? And I was reminded of a paper that I wrote when I was half my age, just when I arrived to Harvard. On the first day at Harvard, a young student from the physics department came to my office. His name is Daniel Eisenstein, and he said, "Would you be willing to be my thesis advisor?" And I said yes, and I gave him a project based on an idea that, perhaps the seeds for quasar black holes, the most massive black holes in the universe, originate in a small fraction of all galaxies that have very low spin. They don't rotate much, and therefore their disks are very compact, so there is less of a barrier for the gas to feed a central black hole. And we wrote a couple of papers on that, and by now, 30 years later, it's forgotten. Most of the practitioners were not even born in 1995. A lot of students are not aware of that, but then I realized that, in fact, the little red dots, these red rubies, you can think of them, in the sky, might actually be these compact disks that are the progenitors of quasar black holes. And so I dedicated all of yesterday, I wrote an essay about it that was published in two places, on Medium and the Brief. And I wrote a scientific paper that I submitted last night about this connection. I connected the dots, in this case, literally speaking. So I use this example to explain the pleasure of doing science. It's understanding how the universe works from a point of view of a kid. I'm just like a child. I don't pretend to be the adult in the room. I just want to figure things out. I don't care about the titles that I acquired over the years. It's really the fun of realizing something new. And the problem is that academia is full of people who pretend to be the adults in the room. They pretend to know the answer in advance. They pretend to know much more than they actually know. And they do it in order to get honors and awards. They do it because they build an echo chamber around themselves with students and postdocs that repeat their mantras. And I do not need to mention examples. You probably know them very well. And my problem is that's not the way science should be done. It's not about our ego. It's not about promoting ourselves. It's about figuring out things. And that's the fun. And actually, it's a great privilege that we paid. So that is my advice to young people. Follow your curiosity. Never pretend to be the adults in the room. Okay, so let me share my screen. And let me give you a fantasy. I'll be very quick in my slides just to allow you to ask as many questions as you want, because that's the fun part. You don't need to listen to me. You just tell me what your questions are, and I'll do my best to address them. And so if you ask me what's my fantasy is to go fishing on Titan. Titan is a moon in the solar system, the only body in addition to the Earth that has liquids on its surface. So Earth, as we all know, has water, oceans, rivers, lakes. Titan has a surface temperature of 90 degrees, a third of the Earth's above absolute zero. And the oceans are made of methane and ethane. And the interesting question is, are there any fish in those lakes, rivers, oceans? And one way to find out is to throw a hook and see if anything catches. Of course, if I were to catch a fish in Titan, it will signify life as we don't know it. Because the chemistry of life as we know it is in liquid water. And we don't know if other liquids support life. So I will not eat that fish because it may be a health hazard. But it will be interesting because the temperature of the universe at large was 90 degrees above absolute zero at a redshift of about 40. And that was after the first stars formed. So that means if an object like Titan existed back then, it doesn't need to be close to a star like the sun. The entire universe would have that temperature. The cosmic microwave background would provide that surface temperature. And perhaps life started back then if we find it on Titan. So the good news is that NASA will have a mission called Dragonfly that will reach Titan. It will not have any fishing equipment, but it will try to look for life, the signatures of life on Titan. I should say NASA is doing the right things, but very slowly and not always in the most efficient way. So when I look at the stars at night, I see a lot of lights out there as if they were the lights from cabins of giant spaceships sailing through space. And I often wonder if there are other passengers in those cabins. That's a very natural thing to think about. So you will hear from your colleagues, mentors, and so forth, they will tell you, oh, thinking about an alien civilization, another thing like us, is an extraordinary thought. Not at all. There are hundreds of billions of stars like the sun. A quarter of them maybe have a planet the size of the Earth, roughly at the same separation. I think it's extraordinary and arrogant of us to think that we are alone. And that doesn't mean that those neighbors are still alive, because most of the stars formed billions of years before the sun. But if they sent equipment out to interstellar space, we can find space trash. And their trash will be our treasure. So only over the past decade, we started finding objects from outside the solar system, big objects. I'm not talking about dust particles. I mean, dust is interesting, but I'm more interested in big objects the size of a person or bigger. And the first one reported was an object discovered by the Pan-STARRS telescope in Hawaii called Oumuamua, which means a scout in the Hawaiian language. It was moving faster than the escape speed from the solar system, and it was flagged just because it passed near Earth. The goal of Pan-STARRS was to discover near-Earth objects. So the only reason they paid attention to this object, and by the way, that's a cautionary remark, is because this object came close to Earth. If this object was on the other side of the Earth's orbit around the sun, I'm not sure we would hear about it. And it was roughly the size of a football field, 100 meters in size. We could not resolve it. What you're looking at is an artist illustration. So why did the artist make it look like a spaceship? It's not, I mean, it actually, the artist wanted to make it look like a rock. But the issue was that as this object was tumbling every 8 hours, the amount of sunlight reflected from it changed by a factor of 10. So that meant that it has an extreme shape. And so people said, maybe it looks like a cigar. And that's what the artist tried to show, is a cigar-shaped rock that is 10 times longer than it is wide. But in fact, when you try to fit the variation of the light curve, that was done in a very detailed paper in monthly notices, you find that, you know, at the 90% confidence, the object must have been flat, actually, not cigar-shaped, but pancake-like. Much better fit to the variation of light. And so what is this object? Very different from the objects we are familiar with, the asteroids in the solar system. And then it was found that this object is being pushed away from the sun by some mysterious force that varies inversely with distance squared from the sun. And it didn't shed any mass. There was no dust or gas around it. The Spitzer Space Telescope looked very deeply, couldn't find anything. So it was not a comet. And the question was, if it's not the rocket effect, what is pushing it? And I suggested it's the reflection of sunlight. But for that to be effective, the object had to be very thin, with a large surface per unit mass. And in fact, 3 years later, there was another object discovered by Pan-STARRS. It was given the name 2020 SO. And 3 weeks later, it was realized, oh, this one actually came from Earth. It's a rocket booster that was launched by NASA in 1966. And it has thin walls. So that's why it's pushed without showing any cometary evaporation. It's artificial. So I had just one sentence in a paper I wrote with Shmuel Bialy, my postdoc, back in 2018. And the sentence saying, well, maybe Oumuamua was artificial in origin. And this paper was accepted for publication within 3 days. If you ask anyone, that's really a record for publishing a paper in the Astrophysical Journal Letters. And the referee was very positive, but as soon as the media got a hold of this subject, I started getting ricochets or pushback from my colleagues. They didn't want to discuss this possibility, which is strange to me because we keep discussing all possibilities about the dark matter, of all kinds of particles that were, by now, we invested billions of dollars and they were ruled out. And nobody says, you know, we shouldn't consider possibilities that are ruled out. You know, it's a part of doing science. So why is an object that looks anomalous, why should we ban the discussion on it being space trash? Now, about 70 years ago, Enrico Fermi had lunch at Los Alamos. And during that lunch, they discussed extraterrestrials. And he said, where is everybody? As if they would come and join him for lunch. Like, you know, this is a question raised by many single people that cannot find a partner. They say, where is everybody? And the advice you give to these single people is, well, you should at least look through the windows of your home to see if there are any people outside, or even leave your home and go to dating sites. That's the way to find others. It's very presumptuous of you to say, I'm so attractive that if there is anybody out there, they will be just next to me when I want it. And Enrico Fermi was a physicist. He should have known better. He didn't build a telescope to search. He just said, where is everybody? The modern incarnation of that is Elon Musk, that last month said, you know, we have all these 6,000 Starlink communication satellites, and none of them collided with an object by an extraterrestrial civilization. Therefore, I don't know, you know, we might be alone. And I say, well, that doesn't make much sense because, you know, we had to invest $10 billion in the Large Hadron Collider to find the Higgs boson. And if we use the rationale of Elon Musk, we could say, well, we haven't seen the Higgs boson with the Starlink communication satellites. That makes no sense. You need to build instruments that would allow you to address the question that you're asking. I actually calculated after he said that a human-sized object, you know, even if it's the same altitude as Musk's communication satellites, it would take 1,000 years for it to collide with one of them. So speaking about Musk, this is a real image of the Tesla Roadster car with the Earth in the background. It was launched in 2018 as a dummy payload on the Falcon Heavy. And it's now in an elliptic orbit around the sun. Astronomers calculated that it may collide with the Earth in 20 million years. And so just imagine this space trash, the car, colliding with Earth in 20 million years. My colleagues, if they were, you know, to be around at that time, and they would not be alerted because this is a small object, doesn't reflect enough sunlight for us to detect it, even with the best telescopes. If it were to collide with Earth and explode as a meteor, they would say it's a rock of a type that we've never seen before. And I'm just saying Elon Musk is not the most accomplished entrepreneur since the Big Bang, 13.8 billion years ago. It's hard to imagine that. There might be a lot of interstellar cars out there. So I was invited by the Polish government to give a keynote lecture on at the celebration of 550 years to the birth of Nicolaus Copernicus. It was February this year, just a few months ago. And I called it the next Copernican revolution, meaning that not only we are not at the physical center of the universe, but also we are not at the intellectual center of the universe. There might be a smarter kid on our block. And just to let you know, Nicolaus Copernicus was a priest. He didn't want to rock the boat. He was a member of the church. And the church argued that the Earth is at the center of the solar system. The problem they had is they couldn't predict when Easter takes place. They got it wrong by a few days. And Copernicus realized that if you put the sun in the middle, the model works. You can get Easter right. So he gave the model to the church. And the church said, great, thank you so much. It really predicts Easter better. We will use this model. But this is just a theoretical model. We know that in reality, the Earth is at the center. And so they banned his book. It became a forbidden book until the 19th century. And he only saw the first publication of the book on his deathbed. He didn't try to be controversial, but he showed a lot of integrity. Just imagine scientists today, just ask yourself, the scientists you know, if they were confronted with this situation, would they instead argue that the error bars on the measurements on the data must be too small, that in fact the church must be right, that there must be a lot of other parameters in the problem? Of course they will. Most of the people I know that practice science would do just that, would justify the church and say that you can accommodate a model in which the Earth is at the center, especially if they are priests, if they are tenured faculty. That's what they would do because that improves their status. But Copernicus didn't do that. And so when people say extraordinary claims require extraordinary evidence, first of all, it's not an extraordinary claim to say that we are not alone. To me, it's an ordinary claim. Claiming that we are unique and special is extraordinary. And my point is that extraordinary evidence requires extraordinary funding. Without investing $10 billion in the Webb telescope, we wouldn't find this first generation of galaxies in the universe. So you need to fund this, you need to seek the evidence. You can't have an opinion and just say, there is no evidence. And obviously, it's a circular argument. If you're not seeking the evidence, you will never find it. So you could always argue there is no evidence and therefore say, I don't need to seek the evidence. But we all know that, like, to find a dark matter, we need to invest billions of dollars. And right now, the astronomy community decided to look for microbes. And actually not look for microbes, but look for the molecular fingerprints of microbes in the atmospheres of exoplanets. And by the way, those molecules of water, methane, oxygen, carbon dioxide, they can be also produced by natural chemical processes. So even if you find them after investing $10 billion in the next, habitable observatory, it may not be conclusive because people will argue forever whether there was a chemical or geological process that resulted in these molecules that we detect in the atmospheres of exoplanets as they pass in front of the star. However, if you find a gadget with buttons on it at the bottom of the Pacific Ocean that was not produced by humans, not only you would know that there is life elsewhere, but you would also know that that life was able to reach an advanced technology and science. And my point is that new scientific knowledge does not fall into our lap. We have to work hard to retrieve it. It's a lot of work, in the past year in particular, as I will describe, I did a lot of work on related to an expedition. It took us a year to plan it. Then we went to the Pacific Ocean for a couple of weeks, and then we analyzed the data for 9 months. During the time that we were doing that, there were a few people that had very strong opinions. They said, you will not find anything. It's a waste of money. It's a waste of time. We don't want to referee these papers, all kinds of statements. And they were saying it as if they are protecting science. My point is that they are anti-science because science is all about collecting materials, looking for evidence, and only then talking about what you find. It's not about expressing an opinion because that's very easy to do. So there is a new frontier of interstellar objects. Actually, before Oumuamua was discovered, there was a meteor, an object roughly 0.5 meter in size that collided with Earth and was moving faster than the escape speed from the solar system. About a decade ago, sensors on US government satellites discovered it. And then with my undergraduate student, Amir Siraj, I basically told him, let's check the catalog of NASA reporting on all the meteors that were found by US government satellites. And this one popped out as having a speed that is well above the escape speed from the solar system. And then Oumuamua, almost 4 years later. And finally, 2 years after Oumuamua, there was a comet. It was discovered by Gennady Borisov, an amateur astronomer. And that one looked just like the familiar comets in the solar system. So some of my colleagues said, well, this one looks familiar. Doesn't it convince you that the other ones are also natural? And I said, well, if you go down the street and you find a weird person, and after that you see a normal person, it doesn't make the weird person normal. Now, the director of national intelligence delivered 3 reports to the US Congress over the past few years, talking about objects that military personnel or the intelligence agencies are unable to figure out in the sky. And this is an unusual admission, either that the intelligence of the US is not working well. I mean, we invest a lot of money in it. The defense budget is approaching $1 trillion every year. And here they give a confession that there are objects in the sky they cannot figure out. They don't know if they are from adversarial nations or maybe something else. And I actually met Avril Haines at the green room of the Washington National Cathedral about 5 months after she delivered the first report. I asked her, I said, you have a bachelor's degree in physics from the University of Chicago, so we speak the same language. What do you make of these objects? And she said, I don't know. So, you know, obviously there is a lot of crap in the sky, human-made balloons, drones, and most likely most of these objects are human-made. But, you know, the duty of a scientist is to check whether, you know, any of them might be from an extraterrestrial origin. Even if 1 in a million is from an extraterrestrial origin, that would change the future of humanity. It will imply that we are not alone. And so I'm leading the Galileo project at Harvard University. And since the first report of the Director of National Intelligence, we started assembling an observatory, a new type of observatory that was never used in astronomy, because astronomers are focused on small regions of the sky. And here we want to monitor the entire sky and look for objects that fly overhead, which are usually ignored. And so we, right now at Harvard, we have an observatory that is functioning and collecting data nonstop. And the data is being analyzed by machine learning software. And we've seen, for example, over the past 6 months, about 500,000 objects. We're now writing papers about them. It's really the first time that was done. There was never a long-term survey of the sky in this way. And so far, we haven't detected anything anomalous. All the objects that we see can be understood, but I should say that was based on examining the data by the human brain. And we already noticed that AI, machine learning algorithms can do better. And they see things that, like yesterday, I looked, I couldn't see an object, but the algorithm found it. So stay tuned. I mean, if we see anything unusual, we'll obviously make it public. But what I wanted to speak about mostly is the expedition that I led to the Pacific Ocean to look for the material left over from the first recognized interstellar meteor. And so when we wrote the paper saying this meteor in the CNEOS dataset of NASA has a speed well above the escape speed from the solar system, the paper was not accepted for publication. The referees said, we don't believe the US government. That's what the referee said. And so at the time, I was chair of the board on physics and astronomy of the National Academies. And in an evening dinner, I explained my frustration. I said, why would astronomers dismiss data coming from the US government? And so through the White House, someone helped me to reach out to the US Space Command, and it took them actually 3 years. They issued a letter 3 years later. You can see it on March 20 left, basically confirming, after they looked back at the data, confirming that indeed this meteor was was coming from interstellar space at a 99.99% confidence. And then our paper was accepted for publication in the Astrophysical Journal. We explained to the editor, look, what else do you want? And so at that point, the government also released data on the light curve of this meteor, so that was helpful. And I decided to lead an expedition to the site that was localized by the satellites based on the light emitted from the fireball of this meteor when it exploded 20 kilometers above the Pacific Ocean. I should say, the fact that it exploded in the lower atmosphere means that it's made of very tough materials, tougher than all the other meteors that were cataloged by NASA. Even iron meteorites would not withstand the stress that this meteor was able to withstand before it disintegrated. Just for comparison, there was a meteor over Spain and Portugal just a couple of months ago that was also cataloged, was moving roughly at the same speed relative to Earth because it came opposite to the motion of the Earth around the sun, whereas this interstellar meteor was came from behind the Earth in its motion around the sun. So both of them were moving at around 40 kilometers per second relative to Earth, but relative to the sun, they had a big difference in speed. So the interstellar meteor was roughly 70 kilometers per second relative to the sun. Whereas the other one, because it was moving opposite to the Earth gave it 30 kilometers per second, and it was moving maybe at 15 kilometers per second relative to the sun in the opposite direction. So definitely the Spanish Portuguese meteor was from the solar system, came from an orbit that was close to Jupiter. Whereas the other one, interstellar, not only that, but it was moving faster than 95% of the stars outside the solar system. And the question is, how is that possible to have such a fast thing? So that's what suggested to me that we should look into it, because it could be a Voyager-like meteor. Imagine our own Voyager crashing into a planet like the Earth. It would appear as a meteor of unusual material strength and unusual speed. Or think about the Tesla Roadster car. The engine may go all the way through the atmosphere and land on the ocean floor. So this is the team that we put together for the expedition, and standing on the deck of the Silver Star ship that we rented exactly a year ago. What we did is built a sled that you can see in the top middle panel. And here we are picking it up from the ocean floor, and it had magnets on both sides that collected magnetic particles from a depth of about a mile. The ocean was a mile deep in that location, or a little more than that, 2 kilometers or so. And we went across the region that was localized as the fireball site by the Department of Defense. This region was 7 miles on a side. And we went 26 times back and forth, like mowing the lawn. And when at the bottom left, you see me jogging at sunrise. I do that every day. I did it this morning at 4 a.m. I usually do it at sunrise. I did it on the ship. And there was a Netflix team, a Netflix crew that documented this expedition. And they decided to join me one morning. And they asked me to run 3 times more than I usually do, 9 miles or so. It took an hour and a half. And then at the end of it, the director said, Avi, it looks like you're running. Are you running away from something or towards something? And I said, both. I'm running away from some of my colleagues who have strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space. So this is the sled, and you can see the magnets. And we would sometimes use a vacuum cleaner, as you can see at the bottom, to suck all the tiny particles from the magnets, or we would scrape them, and then dry them up and put them under a microscope. And most of those particles were volcanic ash, of no interest. But then after 6 days, we started seeing in the microscope images, those metallic marbles. You can see them here, very distinct from the background sand. And every day I would publish a diary report on medium.com. And you know, these diary reports were read by millions of people around the world. They were translated. Get very interesting emails, like, for example, from someone in Denmark who said, you know, I just had a stroke, I'm in the hospital, and reading your diary reports gives me a reason to live, because it's the way science should be done. It's inspiring. And I was really moved by this email. And my daughter said, well, you know, these look beautiful, these molten droplets. Would you mind taking one and threading it on a necklace for me to wear? And I said, well, it's impossible because they are less than a millimeter in size and they're made mostly of iron. And so we eventually shipped the material that we collected over 2 weeks. You can see the case on the right-hand side. I shipped it by FedEx because I didn't want to risk it being stopped at customs. And then I brought it to the laboratory of my colleague at Harvard, Stein Jacobson, who is a world-renowned geochemist that has the best equipment in the world, the mass spectrometer and electron microprobe to analyze those molten droplets that we found. And he is standing next to me on one side. On the other side is Sophie Bergstrom, a summer intern. She came last summer to shadow me because she wanted to become a science journalist. And at some point she asked, could I help you with the science? And I said, of course, and gave her tweezers and a microscope. And she actually found 600 spherules in our sample. So she found most of the spherules we had. We had altogether 850. And so I gave her the honorary title, the Spheral Hunter. And actually she came, as a result of this experience, she decided to pursue a career of a scientist. So she wants now to be admitted to a graduate school in astrophysics. And she's spending this summer as well at Harvard. When we stood for this photo, she said, Avi, you are so short, because both of them are quite tall. Anyway, so most of the spherules that we found, you can see on the left, these are called the primitive, and they are of a type that is known from the solar system. Actually, there are various types, there are various classes of those, but then we found 10% of the spherules to be of a very unusual type. We call them differentiated in terms of their elemental abundances. They had a chemical composition that was never reported in the scientific literature. And here is an example from one of them. So what you're looking at on the horizontal axis is the chemical elements from the periodic table, ordered by volatility. So elements on the right side are volatile. They can evaporate, can be lost very easily in an explosion, as a meteor has. And so indeed they are missing in those, and so that indicates that they resulted from an explosive process, most likely a meteoritic entry through the atmosphere. But the most interesting feature is that, I mean, the elements here are compared to what you expect for the composition of the primordial material that made the solar system. These are called CI chondrites. One means that those are, you know, that the material is from the solar system. And in fact, I just looked, there was a paper posted in April this year from the team that analyzed the material that was retrieved from the asteroid Bennu by the OSIRIS-REx mission that landed on it, brought some material back to Earth. And then this material was analyzed. In fact, you can see a diagram very similar to this one. And it shows, you know, all these elements hovering around one. Because Bennu, this asteroid, came from the solar system. So you see, indeed, that the element abundances are very similar to those you find in the sun. And by the way, CI chondrites are a good representation of what you find in the sun, because the sun was made of this material. So anyway, what we find is some elements are up to hundreds of times more abundant than the standard solar composition. And that includes elements like beryllium, lanthanum, and uranium. So we call this composition Belau type because there was no name for it in the literature. And it doesn't match what you find in the Earth's crust, on the moon, Mars, asteroids. And I published a paper trying to explain it from a natural origin. And actually, if you imagine a planet like the Earth and you bring it close to the sun, it will not get disrupted by the tidal gravitational force, simply because the mean density of the sun is 1 gram per cubic centimeter. It's less than the density of rock. So the sun does not have a strong enough gravity to disrupt the Earth. Of course, once the Earth enters the sun, it will be evaporated by the heat that is deposited on it. But if you consider the most common stars, the sun is not a common star. The most common star is 10% of the mass of the sun, like Proxima Centauri next to us. And such a star has 1/10 of the mass of the sun, 1/10 of the radius of the sun. So the volume is 1,000 times smaller than that of the sun, and therefore the density is 100 times higher than the sun. The most common star is much denser than the sun by a factor of 100. And that means that it's denser than rock. So if you bring a planet like the Earth close to the most common star, it would spaghettify the planet, create a stream of rocks, most likely molten rocks, because they are heated by the illumination from the star. And, you know, if such circumstances take place in protoplanetary disks, which they should, then we should get interstellar objects. And we calculated that actually the speed that you will get from a disruption of an Earth-like planet by a dwarf star is 60 kilometers per second, like this meteor that was seen.
So Avi, maybe we can aim for finishing in maybe a few minutes to have time for discussion.
Yeah, I'm about to finish.
Great.
So just a couple of comments. You know, some people claimed, well, maybe these spherules were coal ash. And we checked 55 elements from the periodic table demonstrating that, no, it's not coal ash. And then some people claim maybe the meteor was a truck, which by itself is a ridiculous claim because the amount of energy emitted by the explosion was a few % of the Hiroshima atomic bomb energy. And it was detected from its light. And that's where we searched based on the localization by the Department of Defense. A truck does not produce a few % of the Hiroshima atomic bomb energy. And as of now, we are planning the next expedition because these spherules cannot tell us the material properties of this object, and we hope to find bigger pieces. The next expedition will involve a robot, a remotely operated vehicle that we will put on the ocean floor and collect bigger pieces from the wreckage of this meteor. It will have a video feed in real time, and it will cost about $6.5 million. So at the moment, we are trying to raise the funding that will be needed for that expedition, hopefully within the coming year. What you see here is a picture of the last day of the expedition with Art Wright, the navigator, who is 86 years old, looking with me at the sunset as we were planning the next expedition. And I really liked Art because he didn't say much, but whatever he said was true and sort of reminded me of my father. And as you all know, next year there is another exciting development. The Rubin Observatory in Chile will survey the southern sky every 4 days. And it will use a camera that has 3.2 billion pixels, 1,000 times more than you have in your cell phone. And so I calculated that it should find an Oumuamua-like object every couple of months. And so there will be many more objects, and this time around, we'll collect more data on them. So a lot of reasons to be hopeful for the next year or two in terms of getting new data, either from the next expedition that we will have or from the Rubin Observatory, finding many more interstellar objects. And the question is, among all the rocks that we might find, is there any artificially made object? And so stay tuned. Thank you.
Great, thank you very much. So we have some time for questions and discussion. So raise your hands here or in the Zoom if you'd like to ask a question. I had a couple of questions. I mean, when I first heard about Oumuamua, I was first sort of skeptical, but then I was thinking, oh, we should build something to chase after it and catch it. How practical, I mean, it's been a while now, but if one really wanted to go after it and find it, would it be possible at all, or has that ever been thought about, Avi?
Yeah, in fact, we wrote a paper about it with my student and members of the Galileo project, and it's much easier to come close to such an object if you detect it when it's approaching the inner part of the solar system, because then you can plan to send your probe along the path of this object and meet it when it's passing through that point. It's much more difficult to chase it. In the case of Oumuamua, we discovered it only when it was past the Earth. And it's possible in principle, you know, if we could raise the funds needed. I mean, that's a multi-billion-dollar project. You know, we could have tried to chase it, but it was moving actually quite fast. One way to think of Oumuamua is that it was roughly at rest in the local standard of rest, which is one of its additional anomalies. Most of the stars move at tens of kilometers per second, like the sun moves at about 25 kilometers per second relative to the local standard of rest, which is the frame of reference that you get to when you average over the motions, the random motions of the stars in the vicinity of the sun. So the sun is moving relative to the local standard of rest, and any other star is doing so with a similar speed. But Oumuamua was roughly at rest. So the bulk of the speed of the solar system relative to Oumuamua was simply because of the motion of the solar system relative to the local star. And so, you know, that means that, you know, in principle, you know, it was moving only at 25 kilometers per second outside the solar system near Earth. It was moving at a speed that we could, in principle, follow with chemical rockets. It would have been very difficult to chase an object like the meteor, but this is not the right approach. Now it's too late. You know, it's already 100 million times fainter than it was close to Earth, because dimming, you know, the flux that you get from an object as it increases its distance from the sun declines inversely with distance to the fourth power. And so it's very faint. There are lots of objects out there. It will be difficult to trace it. You will need to put on your spaceship, you will need to put a big telescope, and it's just not practical. But we should not be obsessed with Oumuamua. We should, you know, if there should be many more objects like it, if you assume that it was not on a targeted mission. Of course, you know, if it was designed to visit the vicinity of the Earth, that's a different matter. But if it's on a random trajectory, the way you expect from space trash or from rocks in interstellar space, there should be plenty. In fact, there should be of the order of 10 to the, I mean, a quadrillion such objects within the Oort cloud right now. And so we just need to find more of them and figure out the nature of this population. And, you know, if it's a thin object, the way I was discussing, it could be a broken piece of a Dyson sphere. It could be a surface layer from a spacecraft. I was not saying that it's functional. I was just saying maybe it's thin. That's all. And just saying that it's thin, you know, nature doesn't make such things, at least the way we see in the solar system. So we will learn something new no matter what. And I should say that the reason I was interested about Oumuamua is a decade before that, I wrote the first paper with Ed Turner and Amaya Moore-Martin, forecasting how many rocks we should expect from outside the solar system, the size of Oumuamua, 100 meters in size. And we just predicted numbers that are orders of magnitude less based on what we know in the solar system. And if Oumuamua was a rock, indeed, there needs to be much more mass ejected from protoplanetary disks than we imagine based on the minimum solar nebula. There should be, at least 10 or maybe 100 times more mass in the debris that is being ejected, which is possible, but it's just something that we didn't know before.
Mm-hmm. Well, I have other questions, but again, people should raise their hands if you have questions. Yes, Oscar? We'll use this microphone.
Thanks for the talk and everything. I understand you were involved with the Breakthrough Stars project. Is that still going on? And is there any developments in it?
Yeah, so that has been going on for a while. It's by now it's 8 years, and the funding was directed mainly to the laser system. The idea is to push a light sail with a very powerful laser, about 100 gigawatt, and the light sail is less than a micron in thickness, and if it has roughly the size of a person, a few meters in size, and it weighs less than a gram, then in principle you can push it within a few minutes to a fifth of the speed of light across a distance that is 5 times the distance to the moon. And that was the concept. And so the first challenge was to develop the laser system, we call it the photon engine. And then the second challenge was to build a sail, to find the material that will give us the needed strength and also high reflectance without getting heated by this powerful laser. And then I should say that was the easiest, actually. We did identify relevant materials and so forth. The third one was communication from a great distance of Proxima Centauri. The idea is it will take 20 years for such a sail to reach the nearest star during our lifetime. And so we could potentially get some images from visiting perhaps Proxima b, the habitable planet near Proxima Centauri. So that was, we worked, various groups were funded to pursue these technologies. It's very challenging. As of now, the funding is sort of moderated, and so it's not clear to me when this will come to fruition. I think it's something that might be pursued in the more distant future, but don't hold your breath as to when it will become practical. Yeah.
Great. Devesh, you had a question?
Yeah. Hi, Professor Loeb. Thank you for the very nice talk. I just wanted to talk about, the point you mentioned earlier about Titan and how you connected it to the early universe. I think they're finding out now.
I have a paper about that, by the way. You can find it.
Oh, great. I'll eagerly read that. So I was just wondering, the planet formation now, have you looked at the planet formation really in the early universe? When the first generations of stars were formed? I think there's some works by Dan Whalen and others who are showing you can even form rocky planets as early as, few 100 million years after the Big Bang. So
yeah.
Do you think you'd like to revisit, let's say, the Drake's equation, the general idea of when life could form? If you are forming rocky planets this early, I wonder someone like you could really change the picture in that regards.
Yeah. So I wrote a paper with a student about the possibility that the first generation of planets were mostly carbon. This is a paper with Natalie Mashian. You can find it from about a decade ago. And that's because the most metal poor stars in the halo of the Milky Way, they are carbon rich, but iron depleted. And so if you had those elements in the abundances seen, potentially you can use carbon to make planets that are made mostly of carbon. And, that could be quite helpful for life if there is more carbon. And one way to check if life could have started very early in the universe is to look for carbon-based planets transiting metal-poor stars. Nobody, as often happens with my papers, and people just ignore them. I mean, I shouldn't say it about all of them, because some of them really have led to big endeavors, including the Webb telescope. I was among the first astrophysicists to suggest that the Webb telescope should be built and looking for the first stars. And now there is another frontier of 21 centimeter cosmology that I helped pioneer. So every now and then people do listen to what I say, but on this one, I haven't seen any search for planets around metal-poor stars, transiting them, because that would tell us something about how early planets must have formed in the early universe. We wrote this paper a decade ago with Natalie Mashian. And then, so you really, for life as we know it, you really need carbon, oxygen that were not produced in the Big Bang. So you need the first generation of stars to make them. And then immediately after that, you can start having planets. And so that doesn't cause much of a delay, because the early stars were most likely massive, with characteristic lifetimes of a few million years, up to 10 million years. So that that is not very significant in cosmological terms, because they formed after at around 100 million years after the Big Bang, and just adding to that 10 million years is not a big deal. So the delay you get from the very first stars to the second generation that was already made out of material enriched by the first stars is not a big delay. And so one can imagine 100 million years after the Big Bang, the first planets forming. And the question is, did they have the nutrients necessary for life? So I discuss some of this in my textbook, Life in the Cosmos, that was published 4 years ago. You can find it. But we don't know. And of course, the way to make progress in science, and even though I'm a theoretical physicist, but the way to make progress is, is to imagine an experiment or an observation that would allow us to figure out the answer. And so in this case, we just need, it's very difficult to look for planets at redshifts above 5. They are so small, you can't see the light from them, you can do transits, but we can look for stars that were born at that time in our immediate neighborhood, and that's what I think is the most feasible way to address your question of when the first planets formed. That was not done yet. And then the question is, could these planets support life? So if we find a carbon-based planet near a low metal, a very metal-poor star, it's, in my mind, we can explore the opportunities for life that is carbon-based on that planet. I mean, I would not be surprised if life started long before we. Now, when you say the Drake equation, you have to keep in mind that Frank Drake pioneered the search for radio signals, the traditional SETI approach. Here, we are not talking about that. We are talking not about radio signals. We are just asking, when could life have started? And could there have been life as we don't know it? That would have changed the equation. But the Drake equation is completely irrelevant because it asks questions about transmission of radio waves, which here we don't care about. And I should say that it's also irrelevant in the context of looking for interstellar objects, because if you find a package in your mailbox, the sender could be dead. I don't need the sender to be alive the way the Drake equation says, there needs to be someone transmitting with the appropriate delay time between the transmission and the reception. But I don't need any, they could have sent packages that are in our mailbox and are dead by now. So it's just like plastics in the ocean. These packages can keep accumulating over time because they're bound by gravity to the Milky Way, in difference from radio signals. So even though people enjoy talking about the Drake equation, it's just in a specific context. And traditionally, the SETI community just focused on radio waves. But now, they are trying to branch out. And my point is, Einstein said that if you keep repeating the same thing, hoping to get a different result, you're not being very smart. And so what I'm
Okay.
suggesting is a different, that's what Einstein said. I'm trying to suggest a different approach for searching, which is not looking for radio signals or electromagnetic signals, which move at the speed of light, but looking for objects.
Okay. Are there any? I have one more question. I'm not seeing anybody else. What I've been learning is that there are a lot of these interstellar objects. It seems like, and so and they're hitting the Earth, or getting close to it, or hitting the Earth. So the traditional search for meteorites, say when they land on Antarctica, have people, there's would you expect something to be showing up in sort of traditional samples of meteorites?
Yeah. So the way we identify the interstellar origin of the meteor that I was talking about is from the velocity, the speed being above the escape speed. And then we are analyzing materials that we hope to find from the meteorite. And if we identify that most interstellar objects, even if they are rocks, they have some special composition, very different from material in the solar system, then one can go to the archive of meteoritic materials that were found over the years. The expectation is that 1 in 1,000 of the objects that fell on Earth came from interstellar space. This is just based on the statistics of, the fraction of all meteors that might be interstellar, based on the 3 examples that I mentioned. So it's about 1 in 1,000, or at the very best 1 in 100. And if you just go to a random place and look at a meteorite, it will very likely 99% of the time be of solar system origin. So it's really, the importance of studying interstellar meteors is to identify their characteristics and distinguish those characteristics from the solar system meteors after knowing that they moved at a speed above the escape speed. And then you can go back and visit, places like Antarctica and look at what you find there. I see a comment by Scott Ransom on the chat. What I was referring to in the Drake equation is electromagnetic signals. I was not necessarily restricting myself to radio waves, but the whole point of Drake was to figure out what is the likelihood of finding an electromagnetic signal from another civilization. And these are the factors that I was referring to as not being relevant in the context of searching for life more globally, either for primitive life that is not communicating in any way. I don't care if it's radio waves or you say, no, I want lasers. It's irrelevant. We are talking about life that could have existed without transmitting any signals. No telescopes, nothing. So that's the question we were addressing. And secondly, there are different ways to search even for technological civilizations. You can look for, and I wrote papers about it, you can look for industrial pollution in the atmospheres of exoplanets. The Drake equation may have some terms that are relevant, but the Drake equation was written in the context of looking for electromagnetic signals. And if you look for industrial pollution in the atmospheres of planets, it's a different calculation. If you look for objects near Earth that may have been space trash, it's a different calculation. If you look for city lights on the dark side, the night side of planets, the Drake equation will not give you the answer. Okay, and I wrote papers on each of these, and you can't use the Drake equation to calibrate the likelihood of finding it.
Well, there are terms in there, aren't there, that it's a time integral of the Drake equation minus those communication terms.
Well, the main factor in the Drake equation is not is the lifespan of the technological civilization.
Yes.
And that is the main factor that you don't know what to assume for it.
Right.
And it's irrelevant in the context of searching for primitive life that formed in the early universe. You don't care how long it lives if you can find evidence for it. Yeah.
I agree with you. Yeah. But then, so you'd want to integrate the Drake equation in time with minus those communication signals, and then add a diffusion term of how often that things are spread out, either by natural mechanisms or.
Well, the other thing I should bring here is an example why the Drake equation is irrelevant in the context of objects, because I can imagine it's a civilization that created a self-replicating probe. What does that mean? Even if one civilization since the Big Bang existed beyond us in the Milky Way galaxy, just one that existed 5 billion years ago, not around anymore, you will never get 0 radio signals from them. The Drake equation will give you 0 because they are not around anymore. That civilization that built self-replicating probes, meaning a probe with AI and a 3D printer that can go to other planets and use the raw materials to recreate another probe of the same type, okay? Just like dandelion seeds. Think about the dandelion flower. It sends seeds in the wind. There is no umbilical cord connecting the dandelion flower to the seeds. The seeds do not transmit radio signals back to the dandelion flower. It's simply the seeds are going there and replicating the DNA of the dandelion flower. And so you can imagine a civilization sending out probes, not getting any signal back from them, no signal, Drake equation equals 0. And those probes are self-replicating. Within 1 billion years, they will fill up the Milky Way galaxy with objects everywhere. Within 1 billion years, because it takes less than 1 billion years to traverse the Milky Way galaxy. I have an undergraduate student just writing a paper on it. If you take Voyager, Pioneer, New Horizons, those probes that we launched out of the solar system will go to the opposite side of the disk of the Milky Way galaxy, the opposite side, in less than 1 billion years. So if you just follow their trajectories within the dark matter halo and the disk of the Milky Way galaxy, you will find that they're on the opposite side of the Milky Way galaxy in less than 1 billion years. And that means that since most of the stars formed billions of years before the sun, that any space trash that was sent by the same means as we are using, meaning chemical rockets, could have made the journey, and they would move at a speed that is 10 times smaller than the escape speed from the Milky Way galaxy, which is locally 500 kilometers per second. So all the rockets that we launched are moving at tens of kilometers per second. They would be gravitationally bound. In difference from electromagnetic signals that move at the speed of light, if they were sent 1 billion years ago, they are now 1 billion light years away.
Yeah, I've always worried about the Fermi paradox. It's, where is everyone? Very good, then. We should wrap up fairly soon. We're a little bit over time, but are there any last final questions? Scott, did you want to mention something about the Drake equation?
No, not really. Just I was saying that the Drake equation is just about communicating, and the lifetime is Avi said, is really important. The lifetime of the civilization, but sending out probes, that is a form of communicating, and so it is. The Drake equation is relevant in that respect. So it is still a useful way of thinking about some of the issues.
Yeah, very good. If you have just one civilization, as I said, with self-replicating probes, it can fill up the Milky Way. You don't need more than that, and so you don't need an equation. It's just a question: does such a civilization exist in our past? That's the question.
I mean, what one might expect these probes to send, communicate with each other with radio. I mean, seems
why? Well, only if they're in close proximity, because you realize it takes tens of thousands of years for signals to cross the Milky Way galaxy, right? Electromagnetic signals. When we look at stars of the Milky Way, we're seeing them the way they used to be tens of thousands of years ago. So there is, unless the probe has a lot of patience, it's really hard to imagine. So only if you have a very tight swarm of tiny probes, they would be able, like a herd, to communicate with each other. But otherwise, each of them will go on its own. And all I'm saying is that nature does it. With the example of the dandelion seeds, they don't communicate with each other, and yet they're able to replicate the DNA because that's what they were programmed to do. And the issue is really about survival of the fittest. And in my view, the kind of civilizations that we might find are those that were able to survive the best in interstellar space, and those are the most intelligent ones. And if you look at what we are doing, we are investing $2.4 trillion in military budgets worldwide. There are 2 wars going on right now. If you open the news, you see only conflicts. That's not a sign of intelligence. We live, each of us lives for less than 100 years, and we are shortening that lifespan by engaging in conflicts. It's not very intelligent. The intelligent thing to do is for for people to come together, work collaboratively, and especially explore where most of the real estate is, which is beyond Earth, rather than fight on territories on this tiny rock that was left over as a residue from the formation process of the sun.
Very good, then. I think we can agree with you there that there's better use for a lot of that funding. So let's thank Avi again for a great talk and discussion.
Thank you.